Does it show up? Yes, I think so.
Yes, it does. It says it's now streaming live on YouTube.
Okay, great. I think then we can get going. All right. Karthik, thanks a lot for doing this. Really appreciate all from the community. We've been doing this community for over 4 years now. We also have an annual conference for the last 4 years called as the Distributed Systems Conference. And pretty active, have had speakers all over the world by this time coming in and speaking. So yeah, I think with that, you should probably introduce and then get going. I think it would be great if you introduce yourself rather than me.
Sure,
just
sure.
reading it out.
Yeah, thank you for having me. Thanks everybody for showing up. Again, please make it interactive. Please ask questions. By way of a quick introduction, I'm one of the co-founders and the CTO. I'm Karthik, one of the co-founders and the CTO of this company, YugaByte, and we are the company behind a distributed SQL database called YugabyteDB. Before YugaByte, I was at Nutanix for about 3 years. I mean, I've been in engineering all my life, so Nutanix for about 3 years working on distributed storage. And before that, I was in Facebook working on like distributed databases again, right? So I joined Facebook in 2007, fortunate enough to have first worked on this project to build a distributed database, which got open sourced and became Apache Cassandra. I mean, back then we didn't know, open source databases would take off. Otherwise, maybe we would have done some things a little better or whatever, but, and then subsequently worked on HBase for a bunch of years, putting it in production for some really big use cases, right? So, and it's not just me, most of the folks in YugaByte have a similar background. We all work together at Facebook on distributed systems and, database as a service and managing this and running this in production at massive scales in Facebook and so on, right? So with that quick intro, let's jump right in. This deck has more slides than necessary, so I'll try to go fast and slow at places. I'm really hoping you'd ask me questions to keep everybody else awake and including myself, right? So this talk is about extending PostgreSQL to Google Spanner architecture, right? So first things first, why the hell do you want to do that, right? Well, we said we started the company and the database in 2016, and the database is fully open source, right? There's just an incidental info. But we said let's go to the drawing board, and in 2016, Spanner was out, Aurora was out. So Mongo was already big, so Cassandra had taken off and was pretty prevalent. So we looked at the world and we said you don't really start building a database or a company unless somebody needs it, right? Why do you really need it? So we went and looked at all these apps moving to the cloud, and we said you know what, there's still a gap, because if you look at the most popular database out there, it was PostgreSQL, right? It's just growing faster than everybody else. Everybody was adopting it. It's even more popular than Mongo, and it just keeps taking off like wildfire, right? But why is it so popular? People moving out of the legacy systems like Oracle, SQL Server, DB2, and including building new applications are picking Postgres because it's extremely open and very, very feature rich and extensible and powerful, right? Yet, if you look at the cloud, Postgres is not built for the cloud, right? It was built before the cloud, before SSDs, before data became big, way back, right? That's not to take away its feature richness, but what would you build a database like if you wanted to make it cloud native, right? So then we looked at Google Spanner and we said hey, Google Spanner was built right architecturally. It's the first horizontally scalable database. But Postgres is not highly available or horizontally scalable. Google Spanner does not have the feature set that Postgres has. So the marriage of these two would look like the perfect distributed SQL database, at least in our eyes, right? So from there, we said, let's compare these two, right? Let's put together what Postgres does. Well, on the query layer, everybody knows Postgres. All of the ecosystems work with it. It has a ton of tools. If you want to get started, you won't go wrong with Postgres, right? That's really all there is to say. But Google Spanner is its own flavor of SQL, right? It comes in with, it's ANSI SQL, but what about ORMs? Are they all well integrated? What about something like a dbeaver or a Table Plus? Can you explore your schema? There's 200 other things that you need to think about, right? And if you look at the SQL feature depth, PostgreSQL is one of the most advanced databases out there, RDBMS, right? I'm not even kidding. So if you're trying to move out of Oracle or Oracle RAC or some of the crazy mainframes or whatever, Postgres has the feature set to back it up, right? In comparison, even basic features are missing or were missing from Google Spanner, for example, a foreign key was missing. It was recently added, but you still don't have things like triggers and various types of constraints, and then you have a long list of things. However, Google Spanner got many things right. It's actually an engineering marvel, right? They had the fault tolerance in HA, where if a node fails, it would automatically, like other nodes would take its spot in like a few seconds. You just add nodes to scale the cluster. You have the ability to do distributed transactions across nodes, and you can do replication, which is synchronous across nearby and faraway regions, right? And including read replicas. It had a bunch of great things. PostgreSQL had async replication, which actually has its own place. It's very important. It's not something we should dismiss as old school, right? So that was really our takeaway. So here's how we reasoned it. We said that the feature set and the ecosystem support is extremely critical for people to build applications. So we cannot compromise on that. So this is what we said. We said we're going to retain the stuff that's good in Postgres. It's strong wire protocol, feature compatibility, and RDBMS depth. And we're going to pick all the good stuff. I mean, HA also, I forgot to circle that, but anyways. But we picked HA and all of that stuff from Google Spanner. And we said, like, we can't really give up on either side in terms of replication. So we need to put the whole thing. And if you're like most people, they were thinking, how the hell are you guys going to build all this stuff? There's a lot of stuff to build, and yeah, it is a lot of stuff to build. But the point is, if you're building a database, let's build it right, even if it takes time, whatever. So we said, let's go ahead and do that. So I'm just going to walk through some 7 key steps. I mean, this is an oversimplification, obviously, but it just gives you an idea, right? So
quick question here.
Yes, please.
A question would be, why not other SQL engines, for example, MySQL rather than PostgreSQL? If you can briefly touch up.
Yes. So 2 or 3 reasons, actually. The first reason was, if you look at the adoption charts, Postgres was on fire. MySQL was stagnant. The second reason is Oracle bought MySQL, and so MySQL actually started being viewed with more distrust. I don't know how much of that makes sense, but it's just what it is, right? Like, I'm not the person making the rules. I'm just telling you what I heard. And the third thing is Postgres is fully open source, like 100% open source, under a very permissive license. MySQL is not. It's under the GPL license, right? And our aim, we think that, like, we at YugaByte, our cultural inclination is towards open source. We think that the database should be free, and we should go and fight with other vendors. And like, even if like Amazon picks up our code or something, we need to fight with them in their turf, not like really muck around with the license and kind of make this a more complicated process for people to adopt, right? So even from that sense, the Postgres ecosystem, community, code base, everything was useful, right? And the most important answer is actually the first step, I think, or the second step. I don't know. We'll see that, right? But great question, Roland. Thank you. I will tell you why. So the point is, we could have built Postgres, we could have built MySQL. The point is, we decided we had to reuse a code base. That was the most important decision. We look at it, I think it probably is step 1 right here. So we first had to decide what features to support. And then we had to decide, are we going to rebuild this database from scratch or reuse the code base, right? Now, all of these databases, MySQL, Postgres, they've been built over 30 years, right? Like, however hard we try, we cannot compress this time frame to like a 2 or 3 years. It's just not possible, right? Like, it'll take you about 10 years if you're really good and you know what you're doing, right? So let's look at what that is, right?
Hey,
so
Karthik, I think the screen share dropped off. Can you please reshare?
Oh, sure. Yes, it did. I don't know what happened. Are you able to see it?
Yeah, it's back. Yeah.
Got it. So I don't know if you saw this. This is the first step, right? Like what features and whether to rebuild or reuse. So our goal was to support almost all the RDBMS features. Don't leave anything behind, right? Because what we found was that's a crazy feature. Nobody uses it. And then it turns out 50 people are using that, and that they cannot live without it. And therefore they cannot move their app because they don't have that one feature, right? We've come across this so many times. So, all the basic data types, joins, recursive queries, built-in functions, queries, all of that stuff, all of the advanced features like partial indexes, table functions, common table expressions, recursive queries, triggers, stored procedures, UDTs, security features like row and column security, all of that jazz. And then the features that let Postgres become extensible, like support for various types of extensions where possible, foreign data wrappers. You can see another tabular list of some of the common features that come up also. So we wanted to support all this. I mean, I'm just giving you the Postgres flavor, but you can apply your MySQL flavor to it and get the equivalent features there, right? So the point is, you had to support a lot of features in order to build an RDBMS that can really stand the test of time, right? So the first problem was we said like, hey, do we reuse this code base, whether it's MySQL or Postgres? That's fine. MySQL we cannot because it's GPL, and we want it to be a very permissive Apache 2.0 license, which means we already are forced to GPL it. And the main question underneath that is, it doesn't matter which code base. Is it possible to make this code base distributed? Reuse is risky because it's a complex code base. Can you even teach it to become distributed? It's a big risk when you're trying to build a project like this, right? MySQL automatically got eliminated here because we couldn't even start with the code base, right? Unless you did GPL, and we didn't want to make the code base GPL and force everybody to, open source whatever they did, and all the complication that went with it. So we said Postgres is, for many reasons, the answer. Now, hopefully that answers your question, Roland. So now to support the ecosystem, right? It should just look like Postgres to any application adopting it. So let's take a very, very common PostgreSQL app, the command line tool, PSQL, and you use pSQL to just list tables. The command looks like /d, right? What do you think really happens under the covers, right? Our first thought was, you know what, we'll rebuild this thing. Not too bad. We'll support the system catalog, like how to list tables, how to list databases. I mean, it wouldn't be too bad. And then we'll add like 4 or 5 data types. And then we keep adding one data type every month or something, and we're in business, right? The problem was, that is how the list tables command looked like, right? You look at it carefully, it has everything under the sun. It has a case statement, which, I'll be honest, I haven't even written that many case statements in SQL myself. So that's like, dude, that's a lot to support. And there's like a where clause, built-in functions, bgcatalog.get user by ID, et cetera, aliasing, there's and, in, everything, order by, like. So we felt like if we're able to support this one command, which lists tables, I think we're pretty much 50-60% there, right? So we said, you know what, let's new idea. This is not going to work. Let's go back and say, let's just reuse. So we actually had done 4 or 5 months of work to actually write it from scratch. And then we hit this and we said, no, it's not, we're not going to get this done in time. So we said, we're going to go back and take the harder route of reusing the code base. And it's paid off, right? Today, if you look at almost all the other distributed SQL databases, they don't support most of these features, because if we had hand-rolled this thing, we would have not even had a fraction of these features. The way YugaByte works is like, we just bring a class of features alive. Like, for example, triggers. Okay, let's just enable triggers. It's not write each trigger by hand. It's just enable partial functions, enable expression indexes. So this really gives us the leverage in building this database in time, right? As if you think about stored procedures, right? If you had to write every line of every stored procedure, it's going to take forever. Right? And not to mention unit tests and design spec and the adoption hardening after users start using it and all of that. So that was step 1, right? Which is actually a rather complicated step if you think about it, with a misstep also. Step 2 was how should we design this thing at a high level now that we decided we are going to use PostgreSQL? Because PostgreSQL is messy code, right? Like, as in, it's not messy code, it's messy code if you want to make it distributed, right? So it has a foreign data wrapper path, it has a native path, it has something else. Like, how do you really architect it? At what point should we cut, right? Now we looked at Aurora. Aurora cuts at the point of the disk, where it stores to the disk and intercepts that and says, I'm going to store it to a replicated disk, right? That's a slightly easier place to intercept, because you're simply taking all the IO to the disk and changing it. But it's very hard to make the query engine scale, right? Because at that point, you're only scaling the storage. All your queries are still going through a single node. So we said, like, this is how it's got to look. We're going to cut it at the row store level, right? So we're going to make PostgreSQL upper half, which does the query processing and everything the same. And it's going to work on top of our own distributed document-oriented database, which is built like Google Spanner, which forms the lower half of the database, right? So the upper half is raw Postgres. We will cut it in the middle, where it talks to a row store, and fool the upper part into thinking it's still Postgres. So this is how the journey then started unfolding. If you think of this diagram as a very high-level Postgres, and it's nowhere this clean, it's pretty spaghetti, but anyways, it's just a high-level idea. The upper part is the Postgres query layer. The lower part is the Postgres storage layer, right? Query layer does parsing, analyzing, rewriting, execution, all of that stuff. Lower part actually writes to disk, right? So write-ahead log, background flusher, vacuum, all of this stuff in Postgres. I don't know how many of you folks are familiar with Postgres. If not, just think it does a bunch of stuff on disk, right? So first step was to retain the upper half, right? And then replace the lower half into a distributed store, right? Which is a document store. So map the Postgres rows into documents at the lower half. And at this point, the upper part simply keeps getting rows from the lower part, and it doesn't know who it's talking to, right? Or at least that's the clean way to explain it. In code, there's like 50,000 places you need to touch. But anyway, so this is what we got done as step one. Now, why do you go to a distributed SQL database? For scale, right? What is the problem when you scale this kind of an architecture? It means that the queries from the entire database or the lower half have to go to a single head node, right? So your queries are always, they're never distributed, right? You can never push down execution. You can't move your execution to where the code, you move your execution to where the data is. You have to keep reading all the data, right? So we said, that won't fly. We need to also take the next step, which is we need to take a subtree of the Postgres execution tree. We need to take a subtree and start pushing it down to the lower level, right? So that would become our step two. I mean, these are long running steps. In some sense, they never get done, right? Like, but you just get an idea of the three distinct set of things we need to do, right? So at this point, you can now execute subtrees in parallel on the nodes and pull it up and do the aggregation on top. If you do a lot of it, we become an OLAP database. That's not the point of YugaByte. It's an OLTP database. So we still want to stay closer to answering very short, fast queries, right? That's really the aim, not to like make a giant execution tree, which is the perfect tree and keep pushing down all the time, right? So just like wanted to call that out. And the third piece is, okay, you've made this plan, but the plan is a Postgres plan. It may not be the best plan for a distributed system. Like there are cases when you may not want to go to the index if it's too far away, or you want to serve a count star from an index if it is nearby. You want to do different things, right? So you want to use not just table level statistics, but geographic location hints and rewriting the query itself for distributed execution. And this would form phase 3, right? And the level of maturity in each of this, and again, like an open source project, all of you folks, if you're interested, please consider working with us in the open source, joining the company, we're hiring, any of that stuff, right? But these are the 3 phases that continue almost ad infinitum, like they never end. And that's the order of maturity as well. The first one, we are the most mature. The second one, much less mature. The third one is really, really new, right? We're very early in the phase, right? So that's the stages of the 3 steps. Okay, so now that we got that level of bearings on how to build this, the next step was, how do you map PostgreSQL internals to a distributed storage layer, right? Yeah, just to make sure no one's falling asleep, let me ask you a question. So how many tables and relations do you think the Postgres system catalog has? Can anybody answer that? I mean, you can take a guess, it's fine. Okay, I'll just answer for you guys. So, sorry, go ahead, Rohan.
Yeah, in terms of hundreds, maybe.
It's in terms of hundreds for sure. I mean, it was a rude shock for us. We said, like, I mean, how bad can it be? Let's just make a table for every relation, right? It turns out it was about 279. And we're like, good God, we just created this database that needs 279 tables to run, and it can't run because it needs 279 tables. So anyways, we had ways to fix it, but the point was, it was not quite expected. So, what did we do? How did we want to map this, right? So we already talked about the upper half and the lower half. We wanted to reuse the upper half. So we said we would map the entire upper half's query layer into a distributed DocDB below. So that would mean each node would be able, like, every piece of data would be replicated, every row would go and live somewhere, and we would keep the system catalog as a special table, which would not get distributed and parsed. So we put all of the 279 tables, each of which has a couple of rows or 10 rows. It doesn't have a lot of data, right? But it has a lot of relations and tables. So we put all of that. We don't even split it up or shard it. We just keep it and replicate it 3 ways. But that was another major piece of work where we had to make the system catalog also highly available. And if you guys know PostgreSQL, you use initdb to start this, right? So it follows a different code path where it simply creates files on disk, and we just had to do it differently. Right? So anyways, so that, and then we started working on the planner, optimizer, executor in order to make it really realize, hey, there's a local node, there's a remote node, there's a cluster, there's a node that's dead, there's a node that's added, there are replicas, there's all of that stuff that goes on underneath, right? And the result of all of this is that the upper half becomes stateless, right? Like now you can go, like if you look at the previous diagram, it means that your upper half can talk to any node, right? And if you run your upper half on every node, then the upper half is effectively stateless. So you have a stateless PostgreSQL as the upper half. You have a spanner-like replicated distributed docdb as the lower half. And the way we did the mapping was every user table would map to a distributed docdb table. We look at how these docdb tables work, but it would map to a distributed docdb table, and and it's be replicated and all of that stuff. If you create an index, it would map to a separate table, right? And the system catalog maps to this special table, which is a group of tables, right? And your app can connect to any node. And you can add and remove nodes at any time because the stateless Postgres will learn about the addition of new nodes and removal of nodes, right? And if you lose a node while you're interacting with the cluster in your app, it's not a big deal because your lower half, the docdb, is fault tolerant. It can actually do quick failovers. And again, we haven't looked at how that is. We've just taken it for granted, but we will look at that in one of the subsequent sections. But your docdb can survive failures, and it's got high availability because a new node takes its spot and starts answering queries. And the upper half is stateless. So just connect to a different node, right? That's all you need to do. If you're connected already to a different node, like in this diagram, you're not affected by the failure. It'll just show up as perhaps high latencies here or there. Maybe not. So, okay. So we talked about how we've reached a spot in taking the Postgres codebase, in getting it to run on multiple nodes, and getting it to work on top of a distributed document store, right? Now, the question is...
One quick question over here. So there are a lot of code changes happening in Postgres as well. So how do you integrate those changes and fixes in your code base? Because when I saw YugaByte's code base, it's more of like a lot of changes are done in the areas which you have taken from Postgres as well directly there. So it cannot be a seamless integration, like just pulling a pull request and getting it done. So what?
Not always. Yeah, it's a great question. So it's not always straight. Like, for example, we actually started out with Postgres 10.4, right? And then we moved to Postgres 11.2, right? Now we are working on moving to Postgres 12.0, right? The real answer to your question is it's not an easy answer. It depends on the feature, it depends on the area of the code, and it depends on exactly what is being done. So there are some things, like one thing that we are philosophically slightly different from Postgres is we don't want to break backward compatibility. Like Postgres sometimes says, hey, just migrate your DB, right? That's it. Okay, fine, you can do that if you're a single node, but if you have 10 nodes running in production with a lot of data, this is going to be very difficult, right? So that is one philosophical difference. The second one, as you said, is we may have changed things in the code base where Postgres has made enhancements or changes. So we have to evaluate those and on a feature by feature basis, and which we do. The good part is a lot of fixes just apply cleanly in still various areas, or with minimal amount of, like, it's pretty obvious how to resolve the conflict if it is there. There are some features that don't, right? And unfortunately, those we have to take them as a design spec for a new feature and build it to the T. This is really how it goes, right? But there's no simple answer, because at the end of the day, we are building a different database, and all of these changes we make are or should be very warranted, right? Not unnecessary. So.
Yeah, I think it's a very nice move to have to support a language which is already popular and deployed everywhere. And then once people start using it and they later on truly hit the limit of scale wherein they would want to use a distributed angle to it, then it's very easy to migrate from Postgres to the YSQL query language that you have. Then in that sense, that's a very nice way of building a product.
Thank you. Yes, exactly. That is the hope, right? That is really the hope, that truly everything in Postgres should be there in YugaByte, until we can make the argument eventually that if you're building this for the cloud, why not start with something like YugaByte? Unless you don't care about scale and you don't care about high availability, then it's fine. In that case, it's completely, that's not the app we are building the database for, right? That's
right.
Yeah.
Thanks.
So, cool. Thank you. Yeah.
Hey, I have a question.
Yeah, please.
Thank you here. So you mentioned that part of execution is pushed to document DB. Like, how does it affect the transactional support of PostgreSQL?
Yes, so we support everything that Postgres transactions have. It's coming in one of the later steps.
Okay.
So we'll be going into how transactions work. YugaByte supports distributed transactions and like transactional semantics and the same and not all the isolation levels. It supports repeatable read and serializable, right? Like YugaByte supports only 2 isolation levels. It's snapshot and serializable. Repeatable read and everything below it in Postgres, like even if it's read uncommitted, it maps to snapshot because we think read uncommitted is, I don't know, kind of wasteful in a transactional database. So we didn't really work very hard to fix that. But we think the useful ones are read committed, repeatable read, and serializable. And we said read committed to repeatable read, hey, we'll just do it the same because the distributed overhead is kind of justified. So those two map to snapshot, and the other one is serial. But we'll look at how transactions work.
Yeah. Okay. Thanks.
Sure. Okay. So the next step is, how do you achieve horizontal scale, right? Like, so we said Google Spanner, you can just add nodes and it'll all work. Now, how does this work in PostgreSQL, right? Like now we changed everything to work with a Postgres front end, right? So it requires a little bit of detail on how DocDB works. So this is roughly going to do that. So on the left, let's start with a 3-node cluster. And let's say you have these 3 nodes deployed across 3 zones, right? I mean, you can deploy it in the same zone, it doesn't matter, but just to give you an example, right? And these 3 zones can become 3 regions, 3 clouds, 1 on-premise, 2 cloud, doesn't matter. It doesn't matter what the 3 are, they're just 3 fault domains, right? And you can change the replication factor to 5 and apply the same principles to 5, but we're just taking an example here that's simple and easy to understand. So the first step about scalability is you need to distribute the data across these nodes. If you keep all of the data on one node and replicate 2 nodes are not doing right, so one node is doing right, you can't really scale the system, right? So you need to get the data into a place where all nodes can do reads and writes for a portion of the data. That's the first step. So the diagram on the right shows you that, hey, in order to do this, you need to split the table up somewhere. You need to split your data. So you create a table. We internally split it up into what are called shards or tablets in YugaByte speak, right? In YSQL speak. So user tables are internally and transparently sharded into tablets. Each tablet is a group of rows. So what this means is that there's one invariant. You don't cut in the middle of a row and split them across nodes. That is a no-no. You take an entire row and you take a group of rows and you put them into a node. Now, sharding is transparent to the user. Now, for those folks who already have grasped what I'm saying, you have controls on how you want sharding to happen in a transparent manner. Like, for example, when you lay out your table, you say that your primary key is ascending or descending, right? Now, in YugaByte, we introduced a third variant, which is called hash. If you say hash, what you're saying is, hey, I'm never going to do range comparison. Like, let's say your primary key was email, right? And nobody wants to do things like, get me all rows where email is between A and B, right? Nobody cares about these queries. You'll give an email, you look it up exactly, right? So in those cases, you can get better distribution with hash, where you pick a random group of rows in each tablet, but you may have like something else like, date, and you may want to do range queries in date. So in that case, we will respect that. So you have different ways of splitting data up, right? That's the bottom line. And YugaByte adds these extras that are needed on top of Postgres in a extensible manner so that you can leverage the full power of a distributed system. Okay, so the first step is these tablets, like each piece of data or each set of rows is distributed across the nodes evenly. Okay. Right now we aren't talking about replication, so let's forget that there's even replication. This is replication factor 1 for now. So you took a table, you split it up into tablets, you took these tablets and you said, okay, I'm going to evenly distribute these tablets across all the nodes. Now, this example, like in the previous diagram, we split the table into 6 tablets because I got tired of drawing all those colored circles, so the cylinders. So in this case, in the first thing on the top left here, you have two of those tablets or those those thingies, those cylindrical things with different colors on there. But in the real world, we do a default of, depending on the table type, anywhere from 1 to 8 tablets per node of the cluster. That's how we started out, right? So it'll look like a lot more. And like I said, I grew lazy and then I just put all this gray color thing in the bottom, but they're all different tablets here, right? So you'll have a lot of tablets per node, right? So you split the table up. If a larger table with more nodes, you split it up a lot more. So you just distribute the data. And it can split on the fly. So it can split dynamically into more tablets. So just like a bunch of ways of doing this. But bottom line is you want to have a decent number of tablets per node. Right? Now, how does the scale actually happens? Right? So if you look at the left diagram, that's the same diagram as the one at the bottom here, which has more tablets, right? So it can really show something to scale. So if you scale the cluster by adding more nodes, so there were 1, 2, 3 nodes here. Here there are 9 nodes. So these 3 nodes, and then you added 2 more nodes in each zone. So what happens is all of these tablets in zone A, they start moving over to the other nodes, and same thing here and same thing here, until your cluster gets balanced by redistributing your existing tablets to all of these new nodes. Okay, and this is transparent, right? You don't even need to worry. So you have a running system, you're doing IO against the system, you add like 6 more nodes, your tablets will seamlessly move in the background. You don't even know your app is just working. Suddenly it's now hitting all the other nodes. Okay, so that's really how it works.
Karthik, one quick question over here. Once this movement of tablets based on the nodes which are present, new nodes are added or being removed from the cluster or a set of nodes, distributed systems. So how will it be mapped to a table? Because there will be some metadata we'll have to store that earlier it was mapped to node 1, now it has moved to node 3. Because so how that thing happens, what is the logic?
Yes, so that is a part of the system catalog enhancements, right? So the system catalog is a special table, like Postgres system catalog has some stuff, YugaByte's system catalog has some extra stuff.
Okay,
so this mapping, it's a very good question, great question. This mapping is stored there, and I think that is extremely important because you may start with all the 3 nodes in one zone A, right? Let me give you a more complex example, and you may say, okay, dude, I don't like the fact that I'm running in zone A because zone A will die anytime and I'm screwed. I want to go like recently it happened, right? Like Cloudflare and Amazon, everybody like got screwed with some failure, right? So something like that can happen. So now you come and say, dude, I want to put nodes on zones B and C. I want to distribute it, right? So you will change. You won't even add nodes for the purposes of scaling out. You will add nodes for the purposes of redundancy, right? High availability. And you will change the data placement policy. You'll change other things, right? Now, what the system will do is it will start moving these tablets across and balancing it across according to your placement policy. There are many reasons why this would happen. So the system catalog updates would not just be which tablet is which node, but also which zone, who can serve, a lot of details.
Right. So is system catalog also replicated? It has to be, right?
Yes, system catalog is replicated. Great question. Replicated, highly available, same characteristics as the rest of the system, because any piece of data in the system is transactional. I mean, it's like business critical, right? System catalog is equally business critical. So everything is, and that actually was one of the big challenges in moving Postgres to a Google Spanner like architecture, one of the many, because the system catalog in Postgres is just a bunch of files, right? Here we had to make it a replicated distributed table,
right.
Which, I mean, code path wise, it's a different code path. So.
Cool.
A Karthik, extension of this question. So while doing this, like while moving the tablet across, when you add a new node, how do you maintain the asset property?
Yeah, so I'm going to answer that question in the transactions section. Okay, so there is a couple of different ways. Yes, I'll answer that in the transaction section. I think right now we haven't even gotten to replicating the data. So
another follow-up question on that. Once this movement is happening, this will happen in the background, and the consumers of this database will not know that such kind of movement is happening. Entries in the system catalog will be updated once this is completed. But if it is in the transition state, that it's in progress, it's not completed, then will the tablets be served for the queries that the user does during this time? That how is it managed?
Yes, so that's a great question. So again, remember that like for the purposes of explanation, I had to split it some way. So we are only talking about scaling and not about replication right now, right? So in this system, right now, whatever we are discussing, there is no replica of any data, right? So that means if you have to move a tablet from node 1 to node 2, you copy the data from node 1 to node 2, and then once node 2 is almost caught up, you stop the writes on node 1 and then you go to node 2. This is how it would happen. So actually it doesn't matter. I can explain it in the context of even replication factor 1. So let's say that this blue tablet wanted to go from node 1 to node 4. Okay. So what would happen is this blue tablet would then get copied into node 4 in the background.
Right.
Okay? And temporarily that one tablet alone would become replication factor 2.
Okay. So you don't.
So that means your writes are going to both guys. Okay. So your writes are going to both guys, and after that you copy the data which is so far contained. So let's say you have 1 to 100 some writes, right? And then you are getting the 101st write when you're doing this. So you say, okay, now I'm going to make this guy replication factor 2. And then you say, hey, from 101, I'm going to come and ask you for the updates, but up to 100, let me copy it out of band compressed files. So node 4 will copy everything up to 100, and then it will go back to node 1 and say, hey, okay, I'm ready to join. And node 1 says, hey, I'm at 110, where are you? I'm at 100, I have everything up to 100. Okay, here, you need to take this other stuff, and maybe he got 2 more in the meanwhile, so he'll start giving everything to node 4. Node 4 now gets to almost 112, and node 1 is at, say, 113. At this point, node 1 is going to say, okay, I'm not going to take any more bucks. I'm going to hand it over to this guy, and there'll be a small blip in the system where it now shifts to node 4. And then node 1 says, I'm just a follower. I'm now the replica. This guy is the serving leader. All reads go to node 4. Node 1 then finally says, I've given up everything. I don't really even need to be here. So I'm going to remove myself from the replication path and delete my data.
So movement is handled through replication, in short.
Yes, movement is handled through replication, and that replication in the next section we will look at it is using Raft consensus at the lowest level to make sure that there is no loss of data. So if you guys are familiar with Raft, it lets you do membership changes on the fly, dynamic membership changes. So this is how it uses it. It uses a group of nodes replicating, and it changes the membership on the fly. So you add one node and then remove one node, then you add one node and remove one node. So you can just move. And so whether you're doing these kind of scale out operations, like adding nodes, scale in, removing nodes, or even changing machine type, right? All of them follow the same principle.
Cool. Thanks.
Okay. So hopefully that answers it, Asif. I think we just thought it's better to cover it now. So, okay, let's keep going. So next step, I think we will go over a little bit of what we just talked about, high availability and resilience, right? We talked about scaling alone. Now we'll talk about availability and resilience, right? So we said that every tablet is, so the unit of replication is at the tablet level. So we already know we have broken up the table into many tablets. We already know we have spread these tablets across multiple nodes, but putting it on one node doesn't give you the ability to survive a failure, because if that node burns up, completely loses its disk, you lose data, right? So that's no good. So what you do is you take every tablet and you put it across 3 nodes if your replication factor is 3, right? And the way the data is replicated across these 3 nodes is using the Raft consensus algorithm, right? What Raft does, it achieves per row consistency. That's the best way to think about it. So you still haven't done anything about transactions across tablets, right? Because you can just do arbitrary transactions in SQL. You took a table, you broke it up into a group of rows. Each row is a tablet. Now within that tablet for a given row, you can achieve high availability. Right? That's what we are talking about right now. How to achieve it across rows generalized, we look at it in the next section. When the leader fails, right, in a Raft system, so you have 3 nodes that are writing, Raft will make sure that you can write to a majority, but it also guarantees transactional, so linearizability, which is the highest form of consistency on any node failure. So if a node fails, in Raft, one of the other nodes can quickly become the leader because they're all hard beating to each other. And so like in a multi-zone public cloud deployment, this is about 3 seconds to detect and assume leadership. Detect failure, assume leadership is about 3 seconds, right? So when the current leader fails, one of the new guys picks up as the leader. We already know that, and only the guy that has up-to-date data can become the leader. So the other guy cannot. So we already know that 2 of the 3 guys have written the data, and one of them is the current leader who just died. So one of the new leaders, the guy who has the most up-to-date has to be, it's like if only one of the guys is up-to-date, he has to become the leader. If both are up-to-date, either one can become leader. It follows voting and all of that stuff. So, okay, so how does this really work? So we said that this is happening at a per tablet level. So now our diagram with just those 2 cylinders, right, for all the 3 nodes, we had that simple diagram where I told you I got tired of drawing that, right? So I got even more tired. That's why I stopped with 2, because when you replicate data, you have to draw a lot more cylinders. So in that example, we had 1, 2, these 2 with solid boundaries here, and then 3, 4, and then 5, 6, right? So we had the cylinders with the solid borders, those 6 cylinders as the original. Now we replicate 3 ways, RF3, replication factor 3, right? So that means all the nodes will have all the data in this example. Of course, if you add a 4th and a 5th, then all the nodes won't have all the data because you just need each tablet to get replicated on 3 nodes, right? So what this does is it takes every tablet, it finds 2 other nodes, and now you enter a Raft consensus group for each tablet, right? So now each tablet works that way, and so failure will now be okay. But note that for any row you write, it is distributed across multiple nodes because every tablet is a group of rows, and depending on which row you update, the tablet leader of that corresponding tablet, whichever node it falls on, is the one that processes the reads and writes. Okay. So in this example, if you get a read that falls off for this on a row which is owned by this yellow tablet, currently node 2 in zone B has the tablet leader, so only it can serve reads or writes. If it fails, one of the other guys will take over in a short period of time, and it will become the leader, and now it can serve reads or writes. Nobody else can. Of course, you can do follower reads, which are little stale, but we won't get into that right now. We're talking about ACID compliant, consistent reads, right?
So,
yeah, go ahead.
What is, I mean, like, what is your thought on using erasure coding instead of replication?
Oh, erasure coding is at the storage level, right? So that is a lower order concept. So what happens is, in this case, so if you take, like, let's go to the previous diagram, it's simpler. If you take a tablet's data and you've written it on these 3 nodes, it means that the tablet's data is replicated 3 times, right? Now with erasure coding, what you can do is you can say that, hey, I don't want to replicate my data 3 times completely. I can use parity and all of this stuff to reduce my effective replication factor to say 1.5 or something like that, right? So that is one more layer below. But the fact that each of those 3 guys can reconstruct the data is still true, right? So the concept is still the same. It is more at a physical level. You can reduce the amount of storage.
But what will be the point of using erasure coding if we are also using replication in terms of raft and at the node level? Then it's
so raft, think of it as a raft works, think of it at the journal level, right? The write-ahead log or the journal level, right? Erasure coding works on the data files. So every time you get an update, you will put it into the journal and then apply it in memory, and then slowly flush it to disk, and then you will delete the journal for whatever got flushed to disk, right? So raft works at the write-ahead log level, where every write is now being replicated to the 3 guys. Erasure coding works after you have flushed the data file to disk, like in same thing in PostgreSQL also, right? Like you write into a journal and then you flush the dirty blocks. So it is at the time when you flush the dirty blocks that erasure coding kicks in. Raft is more at the journal.
Okay.
To make sure that the data makes it to all nodes and is persisted in a way that you can rebuild.
Okay, cool. Thanks.
So because the write-ahead log will be small compared to the total data file.
So this write-ahead log will not contain the data, it will just contain sequence of updates. Is that?
No, it will contain the data, but it will get deleted. So it will contain the data. So every write on a node, it gets applied to the write-ahead log first, persisted, and then applied in memory, sorted in memory, flushed into disk, right? And the disk is made. So the minute it gets flushed into disk, you don't need it to in the write-ahead log again, right? So you just delete that one. Yeah. So it's like constantly getting ingested, and then you keep deleting the log. So only the last n updates that haven't made it to disk, they'll stay in the log, or like that type of stuff.
Yeah, right.
So okay, so so the key things to note here is that the tablets are replicated across 3 nodes, each tablet, and this can survive a node or a zone failure. We'll look at how. And the follower tablets or the replica tablets are also balanced across the nodes. So in a 3-way replicated cluster, each node should have 1/3 tablet leaders and 2/3 tablet followers, because of the replication. Now, you have controls to say, hey, I want to move all my tablet leaders to zone A or zone B or zone A and B. You can do all of those kind of fancy things, but I'm just giving you the default, right? The simple thing. Right? So, because if A, B, and C are far away, you want to keep the serving close to the app, so you can do things like that. Okay, so the same system, so this system that we did with 3 nodes, now if you scale that same diagram to 9 nodes, again, remember that you'll have a lot more tablets in the real world, so it won't look like there's only a couple of nodes in each. It won't look like that. It'll look really like more dense. But anyways, so then what we did was we took all of these tablets, whether they're leaders or followers, it doesn't matter. And then we applied the thing that you want your leaders and tablets. First, you want your leaders to be balanced across nodes, and then your followers to be balanced across nodes per table. So that's really what you want to do. So now let's say you lose a node. Right? Let's see what happens in this system. So let's say you lost node 4, which was the tablet leader for this yellow tablet. Then the raft algorithm will then kick in, and these two guys, these two other yellows will then race to say, we need to start a new leader election. This guy's not responding. Let's now create a new leader. And in a public cloud, in a multi-zone deployment, in about 3 seconds, a new leader is elected. So in this case, let's say node 2 got elected as the leader. So now all the writes can go to node 2. So if you tune your app latencies properly, you can actually get away without any failure in writes. Just elevated latencies. If you also lost this other color, whatever this color is, purple or whatever that color is, so you lost that color, that is a follower though, right? So because if you're not doing follower reads, you're really not impacted. It's just like a active standby that you lost. This guy who's the leader has another active standby here, so you're fine. So if this guy dies, this guy can pick up, so it's really not a problem in the system. So right now, this guy will just nothing will happen for this other guy. Right? During the 3 seconds where this guy failed and the other guy didn't take over, the database will be unavailable for writes for all rows that belong to this tablet. So that's why it's not a perfectly available system. It is still a consistent partition tolerant CP system with high availability because it's 3 second downtime. But if you're doing follower reads, you're fine. You can serve it out of one of the other guys. It's okay. Stale reads are fine, but like transactional reads and writes are out in the system. You can't do it for those 3 seconds for the set of tablets that are leadered on the node that just died. Okay. So let's keep going. So how automatic resilience works is that there's a flag, which is 15 minutes by default. If after 15 minutes, this node doesn't come back, right? What we say with YugaByte is like, hey, looks like this node isn't coming back. 15 minutes seems like a good enough time. You can change that number, but we just made it 15. Then we need to re-replicate the data because now you are susceptible to, if you have lost another node, you can actually lose data. Like in this example, now this purple color and this yellow color, these two guys have only 2 replicas in the system, right? They don't have 3. So if you lost another node, which has a yellow or a purple, now you are in trouble, right? Like you don't want, because you can't survive in another failure. You can't write if you don't have a majority. You need 2 locations out of 3 to write. So what we do is we pick nodes in the same placement policy. So in this case, let's say you said you wanted 1 copy of data per zone, right? So we'll pick a couple of nodes in the same thing. And now this yellow is re-replicated here. This purple is re-replicated here. And now the system is back up to replication factor 3 for all tablets. And if this node comes back up, it will automatically catch up. So the system will say, hey, in this zone, these guys have 3 and 3, and this guy has 0. So it's time to move something out there. So let's move a couple of tablets from 2 different nodes there to evenly balance. And you could have maybe blue and green move here. You could have different guys move here. That's okay. So the tablet leaders, followers, everything is auto rebalanced when the node comes back up. Now, if you lost a whole zone, it's not very different. So if you lost the entire zone in this this diagram where you had here, you would lose all these guys. Now this node in this example has only followers, so it doesn't matter. This guy has a leader and this guy has a leader. Those are the only 2 that are affected. So exactly the same way, this guy will fail over to somebody, this guy will fail over to somebody in 3 seconds. So in 3 seconds, even if your entire zone is dead, you will get new leaders that are automatically re-elected. When this comes back, your re-replication will happen. And if it is under 15 minutes, we will reuse the same data. If it is over 15 minutes, we'll throw away the data and restart it. So just whichever way we go.
So one question, Karthik. The reason why we choose leaders per tablet is to make the granularity level smaller rather than keeping a leader per table, because table can be of huge rows.
Correct.
But on the contrary, what can happen is, so what is a tablet size? What can happen is a single node can contain can be a tablet leader for multiple tablets belonging to the same table as well. So in that case, would grouping those tablets make sense?
So the way we do this is actually a very, very good question. So we first balance the tablets across node per table. Then we apply the algorithm per node. Right. Okay. So because the thought process is simple. The thought process is you have tables that are write heavy or read heavy or both. Right. But you probably don't want all the write-heavy tables to be on one set of nodes, and you don't want all the read-heavy. You want to distribute because you want to use the disk well, you want to use the memory well, all of that stuff, right? So we first do the distribution by table so that you disperse the table well, and then you apply, hey, if I dispersed all my tables, but then I have too many tablets on one node from different tables, so let me now spread that out. So it's a double thing that you do.
Okay.
Okay. And by the way, there is another corollary to this. You could have many small tables like the system catalog example. In that case, we allow multiple tables to go into one tablet. This is called a co-located table or a table group in YugaByte. So you are doing the reverse is also possible. So I mean, I don't want to bring that up, but anyway, just since it's come up, I'm just explaining.
Cool.
Okay.
Hey, Karthik, a question from you, Aditya.
Yeah.
So in databases like Cassandra, rebalancing often has a heavy penalty on the load on the node in which are streaming the tables in, and that often causes availability issues as well. So have you done something to mitigate that?
Yes. Great question. I mean, I don't know if you know, but YugaByte supports another API, the YSQL API, which is Cassandra compatible also. Anyways, that's a different direction, like not the topic of the meetup. So I didn't, but happy to answer questions there. But specifically to answer your question, Cassandra is not an ACID compliant database. When we built it for search. So it's eventually consistent. That means it writes to a majority and reads from a majority, but you can never say any one node has all the data. So if you have 3 nodes, the first 2 could have the value A, the next 2 could have the value B, and the first and the third node could have the value C. So in this kind of a scenario, no single node has all the data, right? That's because it's optimized for availability, not consistency, right? So in this case, if you added a 4th node and you wanted to move the table to the 4th node, you have to scan the data through the database across all the replicas, right? So if you have, let's say, a terabyte of data that you're reading, and it's replicated 3 ways, and it's compressed, right? Like, let's say it's 5x compression. So now you would really need to read that 1 terabyte of data across 3 replicas, which becomes 3 terabytes, and then expand it 5x, which becomes 15 terabytes, in order to move that 1 terabyte of data to the other node. Okay, if that makes sense. You need to read, resolve, uncompress everything. In YugaByte, however, because we have taken that 3-second downtime, the advantage that you get in exchange for that is, you know, that there are nodes, every node is consistent up to a certain point in time. It's 100% guaranteed by Raft. So we simply go and copy the data files. So it's not even competing with the app or with the database for any of the scans, no scan, no compression, decompression, nothing, right? So simple SCP, I mean, it's like SCP internal to the database. So bottom line is, it's going to be very highly performant and efficient, even if you're adding nodes under stress. And yes, we have tested that a lot. And that's one of the top reasons why people end up using the YSQL API for very dense workloads when you want to put a lot of data per node. Okay. Okay. So yeah.
This side. So you talked about the node going down, and sometimes you have to replicate the data, completely move the data to another node, right? 3 seconds is for figuring out the health check is failed. But how much time, like, do we cap also on, like, how much data goes into each tablet, so the movement is the time for the movement would be less?
That is your configuration thing. So there is a trade-off here. There could be use cases which are very valid, where you know that you're okay taking the occasional hit of the disk completely burning up. Like for example, you don't have EBS, you have NVMe drive, but your re-replication is quick. There could be other scenarios where you're using like an EBS, a replicated disk, right? But you want to put, say, 10 terabytes per node, because your storage is much more than your queries. Your queries are not that often. Like there's like IoT example, for example, right? Like an IoT use case where you keep getting data, but maybe you're only reading the last 1 day or 1 week's worth of data, but you have 10 years of data stored, right? So in such scenarios, you want to pack the data heavily, right? So this is really a deployment concern on like how many nodes and how tightly you pack it and how much in parallel you want to replicate. So there's a lot of knobs there that you can tune. Okay, makes sense? Okay, so I think it's like 8:56, so I don't know if I'll get through the whole thing, but that's fine. At least we can continue even after. Anyways, the simplest way to characterize Yugabyte is in a multi-zone public cloud setup. RTO is 0, RTO is 3 seconds. RTO obviously is only for a subset of rows, but nevertheless, when characterizing a database, let's not split hairs, right? So 3 seconds after the outage, you should be able to revive. Now, if you go to faraway regions, your 3 seconds will increase. So if you're doing like very far away regions, this could become 30 seconds because you don't want to unnecessarily cause outages for short partitions. So you want to give more time to detect failures, right? You want to be easier on the system. So just something to keep in mind, that the RTO actually depends on the distance, the replication distance, right? So finally, I think the last, or one of the last steps, the last step is actually async replication, but one of the last steps is distributed transactions. Okay, I'm going to go relatively fast here because it's a complicated topic, but again, happy to answer questions in the AMA or something if folks have it. On the distributed transactions, I mean, simplistically, you're updating two generic rows. The thing is, they can belong to different shards, and the shards can belong to completely different graph groups. So what you're really looking at looks like this. So you have many nodes in a cluster, you're updating 2 rows, like transactionally, that goes to one group of nodes and another group of nodes, and this is what you really need to do. The problem is all of this has to happen at one atomic time, right? And the real problem is nodes never agree on time without an atomic clock, right? So, and most of us don't have atomic clocks, so that's out of the question. So for those of you who want to know what an atomic clock is a very highly available global clock that all nodes in the cluster have access to, but it gives you a very tight error bound, right? So in the case of Google Spanner, for example, it gives you a 7 millisecond error bound. That means that no 2 nodes will drift more than 7 seconds between each other. And the rest of us poor folks in the world, we can only do as good as say 150 milliseconds or something with NTP. And even that's not a guarantee, right? So this is really the question on how do you do a distributed transaction when you don't have atomic clock guarantees. So Yugabyte uses something called a hybrid logical clock. So it uses this NTP, which is coarse. It can be 150 milliseconds. That's okay. But within this 150 millisecond sync interval, it uses a Lamport clock. So it's a logical component, which says every time I do an operation, I'll bump up a number. Every time I get an exchange from another node, I'll synchronize my time with that node, right? So as long as you can detect causal chains, this is going to be very effective. In places where you cannot, we will declare that there is a conflict and force one of the transactions to restart, about transparently restart, surface to an error to the user, and so on. Now, a lot of people, if you just think about it at a high level, it sounds like, oh, atomic clocks are good, not 7 milliseconds, and here it's like bad, right? But it's never that black and white. Like, remember that conflicting workloads can be present even in a single node RDBMS because it's just the nature of the workload. So what really needs to happen is you need to be performing updates that are conflicting for an overlapped set of keys in that window of time without the nodes actually having any exchange in RPCs in that window. So this is a very low probability set of events. Of course, you can write a pathological workload that will really exploit it. But the question is, do your real life workloads actually hit a lot of issues in this case? And what we have observed is it's not the case. So it is actually possible with a lot of optimization to really derive good performance without really getting affected. So what is the distributed transactions philosophy in YugabyteDB? It's designed like Google Spanner. It's based on two-phase commit and uses hybrid logical clock for time synchronization. Why did we choose this? It's better scalability as opposed to having a single timestamp oracle and everybody going to that timestamp oracle, because if you're using the multi-region deployments, you will have to deploy the clock authority in a single region, which causes issues when you're partitioned or like all sorts of problems. Now, our assumptions in general are that global deployments will get popular. So having a single timestamp authority is a bad choice for future-proofing your workload. And clock sync in the cloud will get better over time. This was written in 2016. Now we have time sync service in AWS and Azure. And so it is definitely heading that way, right? And we don't want to use atomic clocks, and therefore we'll use HLC, a hybrid logical clock. Okay, so now all of that out of the way, the idea was to not have a single point of failure or a bottleneck in the system. So no single time issue authority. Any node can handle a transaction. The transaction is actually stored in a table. It's called the transaction status table. It is also a distributed and replicated table. and it tracks the state of all the currently active transactions. A transaction can have 3 states. It can be pending, committed, or aborted, right? The name pretty much implies what it is. And only committed transactions can do reads. It can be served in reads. If it is aborted, it's ignored. If it is pending, then you can think of it as a persisted lock. You have to apply your conflict resolution rules if you see there's a transaction in progress that's touching a row. So overall, a client never sees inconsistent data. I think the question of isolation levels. YugaByte supports 2 isolation levels: serializable, which detects read-write conflicts, and snapshot, which detects only write-write conflicts. Right? So serializable is the highest level. It maps to serializable, and Postgres behaves the same way. And snapshot maps to all the others lower than serializable. Right? So So it is actually stronger than the ANSI SQL repeatable read, what snapshot offers you. But it maps to, we just mapped it to all of the others. So it's slightly above repeatable read, but below serializable. So we figured it's just good to map it to serializable. Sorry, to repeatable read. And read-only transactions are lock-free. So there's a number of ways with MVCC to ensure that you don't need to lock out rows and all of that stuff.
So one question over here, Karthik. If a transaction is spanning 2 raft group, as you pointed out, and update to one of the raft group has failed, so will the transaction be aborted and retried, or?
Today it is aborted and retried. So this goes to concurrency control. YugaByte today opts for optimistic concurrency control, which means, so there's 2 reasons it could have failed. It could have failed because another transaction has committed or another transaction is in progress. It could be either. If the other transaction is committed, it's very simple. You have to abort. There's no way around it. Right. If the other transaction is in progress, you have 2 options actually. You have 3 options. You can abort the other guy, or you can wait for the other guy to complete and then go finish, right? So the first 2 are actually optimistic concurrency control, and that's what YugaByte does. So we flip a coin and we abort ourselves or the other guy. But we are working on, what is in progress right now is the design for pessimistic locking, which is let's wait for the other guy, put it into a queue, and but you have to do deadlock detection. You have to do a few more things, but it is useful. So that is something that we are working on. But again, note that YugaByte supports explicit row locks. So the way we handle that is we actually issue each transaction a priority level, and we allow priorities to get issued in 2 classes, right? High priority transactions and lower priority transactions. Explicit user locks are higher priority, and they always win against any of the others, right? So your explicit row locks actually work without pessimistic locking. Or you can call it pessimistic locking or not, it's up to you. I mean, it depends on how you look at pessimistic locking. Is it the locking part or the waiting part? But okay. So bottom line is, in YugaByte, app will have to, as it stands today, app will have to handle restarts, which is probably true even in SQL. Eventually it can give up, but here the probability will be a little more. So you have to be more aggressive about handling restarts because of the optimistic side. Okay, so how does the write path work? So we'll go through the most generalized thing. We do a number of things here to optimize the performance, but let's say you're updating 2 rows, K1 and K2, right? It hits some node, right? That node becomes the transaction manager. It writes to the transaction status table a record with the transaction ID, which says it is in progress. Now in practice, we squish these 2, put them on the same node and pre-create the transaction record so we can get away without this, but just optimization detail, right? So let's just go through the theory. Then we write to each of the nodes which own the tablet leaders for K1 and K2. We will do what is called a provisional write. The provisional write record will contain the update along with the transaction it is attached to. So if somebody else comes and does a read here and finds this guy, he needs to go chase this transaction ID in the status table and look up what is the state of the transaction. If it is committed, he can serve. If it is aborted, just skip. If it is pending, apply your conflict resolution rules for based on what is the isolation level, all of that stuff, right? Like what is the operation, isolation, all of this stuff you'll have to think about. All of this is replicated using Raft, as you can see here. So it's all highly available, yada, yada, all that stuff, right? So like that's generally the idea here. Finally, so this write itself may encounter other provisional records, in which case you will not be able to acquire your provisional records. You may fail, or the other guy may fail. But as long as you're able to acquire all the provisional records, you flip the transaction status to commit. the timestamp at which this guy gets flipped to committed becomes the timestamp of the transaction. Since everybody chases this transaction status, they will know the timestamp of the commit. So once that commit is done, you can safely respond to the client. But in the background, we also flush down the value of the commit timestamp down here to finalize these provisional records. So you don't have to keep doing this chase indefinitely. So this is the more distributed transactions path. Note that if you are doing a single row update, you skip the whole thing, go straight to the tablet reader and make the update. So we don't use the generalized distributed transaction where you're able to do straight up insert, update, upsert, like, insert on conflict, all of that stuff we can start pushing down more aggressively. Okay, last topic is async replication. So YugaByte actually is the only distributed transactional database that supports async replication also. Some NoSQL databases do it. Single node RDBMSs do it. The distributed SQL databases don't. They only support synchronous replication, right? But what we found is with two oracles joined by a golden gate, that type of topology, this is really, really useful. And because replication is built into the database, we said, hey, let's build what we call X cluster or cross cluster replication, which is async replication into the database itself. So the way this works is you can replicate between two or more decoupled YugaByte clusters. So these are all synchronous clusters that can replicate to each other. They'll consume changes from each other. Obviously, you have to ensure all of your RDBMS red flags apply here, which is the schema has to match. Don't do crazy things. Don't create unique constraints. All that stuff matches, like the same thing here. Architecturally, the building block is similar to generalized change data capture also, because a cluster can now emit its changes, but we have right now only focused on applying those changes to a target YugaByte cluster. What are the guarantees? In order delivery of a row at a tablet level, but per row. It applies to non-distributed transactions. Ordering across tablets is not guaranteed for non-distributed transactions, which means that you could have inserted row 1 and then row 2 in two different tablets. You can actually get row 2, row 1 because they are not connected. Right? This is not a transactional update. These are two independent updates. We feel this is okay. Right? Like, it's okay that you inserted 2 rows as part of 2 different transactions and you get it out of order. That's okay in async replication. It's not a big deal. The other part is at least once delivery of changes. So that means that you won't lose anything. Monotonic updates. It means if you've seen an update, you won't go back and get an older update that you missed. You'll only get further updates into the future. Yeah, that's what it says. And we do a periodic no-op to bump up the timestamp up to which the destination cluster is caught up. So on transactions, the last writer wins semantics is applied. So if you have 2 guys getting updates for the same row, you will get timestamp independently assigned. These are not hybrid logical clocks synchronized because they're 2 independent clusters. Irrespective of the order in which these writes happen on these 2 clusters, the one with the higher timestamp will win. It's just that. That's all it says. If you have a constraint violation on the sync, well, bad things will happen. So, I mean, this is again no different from RDBMSs. Right? Okay, so we had a lot of discussion about exposing this conflict to the end user. It's more of a headache and it's more work on the database. So we have deferred it and said we don't want to do this right now. So bottom line is don't do such things and push it to the edge. It's better to be very clear if you're doing async replication. Right? Okay, so we are working on distributed atomicity. So the way this would work is today, all of the updates get sent as a part of a transaction to the other side. They are immediately applied, but they are applied with the same timestamp. So if you change 3 rows as a part of a transaction on the source cluster, the 3 rows get applied at different points in time, but with the same timestamp on the destination today. What we are working on for the future, though, is that these 3 will get applied in a wait to commit state until all the 3 have landed, and then they'll atomically flip to visible. That's not done yet, but it's in the roadmap. Right? Yeah, these last set of features are in progress. So yeah, I think you can replicate from an M node cluster to an N node cluster. It doesn't have to be 1-to-1. You can have different sized clusters on the 2 sides. I'm not going to go through this example. It's too much in the details, but you can do unidirectional and you can also do bidirectional. Right? So it's just reverse the streams, and now you get bidirectional. So you now get low latency writes and eventual consistency between. And this is very similar to your RDBMS semantics, but each side, instead of a single RDBMS, you have a single cluster. So I think that brings us to the end. I think we are 10 minutes over time, but that's fine. So we are a fast-growing 100% open source project. So if you folks are enthusiastic, feel free to join. Help us out, spec, test, build features, try out whatever it is, documentation, anything helps, everything helps. But it's resonating with a lot of people. I'm very, very happy to see that our number of clusters, we actually just crossed recently 500,000 clusters, like 500,000 clusters installed in the wild, which is really awesome. Our Slack users just crossed 2,000 users in like just a year and a half to 2 years, which is like, again, amazing. And so, yeah, things have been going well. Like we are now deployed in production for business critical data across many users and customers. So if you like what you heard, give us a star. We love it. Join our community on Slack. We'd love to interact with you. We are hiring. So if you're interested, looking, feel free to drop me a line, or if you just want to work with us in the community, great. Either ways, whatever works. Another call out is we are doing a we've been doing our second distributed SQL summit in North America. We just did it in September of this year. It was a huge success. We had 750 people attend, 26 speakers. Like we had, like, for example, one of the keynotes was the creator of Kubernetes, Joe Beda. Another of the keynote was a professor out of UC Berkeley who's working on stateless systems and Lambda and stateful, like how serverless and stateful work. So a lot of good speakers came, and a lot of demand from the Asia/India side. So if any of you folks are interested in talking, our CFP is open. Please consider putting in talks. At a high level, we're simply thinking of cloud native app development, cloud native databases, and if you have your journey, and it's not even about YugaByte, it's vendor neutral. It's about distributed SQL. So anything that's related to it, whether it's like running stateful workloads on Kubernetes, it can be like in any of those areas, right? We would really welcome contributions. So it's in January, I think Jan 21st or something like that. But yeah, feel free to again drop me a line for that. So yeah, that's all, folks. So